Hello everyone, and welcome to part 2 of Autotrain. In order to build this clock step by step so that everybody gets an idea of how Autotrain works, we ought to take a look at the Autotrain module itself. First of all, it only works on the round gear module. You can use it with any type of gear except for bevels, but take note that if you try it with a knuckle or helicals or herringbones, it's going to take a long time to generate its output. There's also very little indication while it's doing its output at the moment, so it may appear to be locked up, but it will eventually complete its job typically. So I would stick with spur gears for now. I was using epicycloidals on the clock. Whatever you have set on this screen for module, DP, type of tooth, and so on, is what will be used for every gear that gets created. The DP and module boxes have changed on the round gear. You can now enter a DP or a module, regardless of whether or not you are in metric or standard measurement system. If you're in metric, things will still stay metric, but you have the option of entering a DP gear. This is in case you're trying to duplicate a gear somewhere. You're a metric type person, but the specs you've been giving are in DP, so you can enter DP directly now. So once you've selected a face width and all the other parameters that you want to use as a standard for your teeth, select Autotrain. Now in Autotrain, we're given a desired ratio, a set of presets, which we will add to over time, a maximum allowed error, a complexity where you can pick 1 pair of gears, 2 pairs of gears, or 3 pairs of gears. You can set a minimum and maximum number of teeth, and then there's an add to projects button and an input rotations per unit button. At the moment, let's ignore the input rotations per unit and simply always leave it at 1. You can pick ratios from the predefined. For example, if we were to pick pi, 3.14, so this means we want to speed up gear train that speeds up at a 3.14 ratio. The output is going to turn 3.14 times for every rotation once of the input. I can select 1, 2, or 3 pairs and do a search. I'm pretty much instantly shown all the possible gear combinations of 2 teeth between minimum and maximum tooth count, which will give you approximately pi as a ratio. And the first entry is error, where you will decide how close you need to be. And if you drag down your slider to the point where it changes from a negative to a positive, that will show you your closest point, which in this case is 0.000000131 off of target. If you use 3 gears, you'll see that you can normally get closer because 3 gears, of course, gives it more possibilities. And if we look at where it switches over, you can see now that it is approximately 0.00001 off. You can also, if you get too many results, lower your maximum allowed error. If we take it right down to a very low amount, you can see I've now narrowed it down to about 7 possibilities, and they all have a error of 0, which means I'm going to get my exact ratio that I'm asking for. Once you have a set of ratios, let's go back to 2 and search for a higher error so that I can actually find one. Once you find a list of possibilities, you'll notice by clicking on one, you'll see a picture of the gears on the bottom window here from the side. This gives you an idea how the pinion and wheels are going to fit together. The way ratios work, let's select 45, 19, 13, 21, and what you'll see is I have a 45 tooth, this pink, meshing with a much smaller gear, a 19 tooth, and then underneath, a 13 tooth, and then under the 13 tooth would be a 19 tooth meshing to a 21 tooth. So the way these diagrams or the listings at the top work is the first numbers before the slash are your wheels, the second numbers are your pinions, and here we're defining pinion as the gear which is driven by, or as a driven gear, where the wheel would be a driving gear. If you add to project, the gears will just simply be generated and appear on the screen, and they will have the proper ratio. You'll notice if I click on the output gear, the screen reports that I have a rotations of master for one rotation of the gear is 0.31928. 29825. Whenever you click on an output gear to see what its ratio is as compared to the master, you're going to get the reciprocal of what you selected. So the reciprocal of pi is approximately 0.319, and that's the proper ratio. Now there's another problem that people face, is you can generate the ratios, but sometimes it's nice to have them match on a shaft. So let's take a look how that's done. If I just select one of the gears here, the end gear, there's a new button called shaft to shaft. And what you're basically telling the system to do is to move that gear to a new shaft. So if I hit shaft to shaft when I have the gear selected, incidentally, I can select the gear or its shaft. It doesn't matter. So I select shaft to shaft, and it'll ask me which shaft would I like to match it to. Well, if I try to send it to shaft 1, which is the middle shaft here, I'll get an error that says I cannot match shafts that are being driven. The two are too close together. I can't move this gear to that shaft, obviously, or it couldn't be driven by the gear which is on it. So now if I hit shaft to shaft and I tell it to move to the original shaft, you can see what happened is the gear has moved, and it's moved to dead center of the first shaft. There is no connecting shaft. If you look at the space, this is an indicator to you that they actually each have their own shaft, or that one is slipping on whatever shaft that you have there. If we simulate, you can see that everything runs, and these two gears are not bonded to a shaft. The reason that this is possible is because the module of this gear that we move, spur 3, has changed. While when we generated the gears, the module was 4.35. Oh, sorry, it was 3. And you can see the original gears have a module of 3. But what these two top gears have changed to a module of 4.35. So the system calculated that if you wish to have two gears of those tooth counts to fit on those two shafts, you would need a module of 4.35. So it automatically re-extruded them, recreated them as that module, and stuck them on two shafts. Now you can always undo if you're not happy with the results of something like that. But take note that you normally only go back 2 shafts. You can go back 3, 4, 5 shafts, but take note of what you're doing, because you could create awfully large gears as they try to match their size to fit on those shafts without moving the original shaft. Sometimes it's worthwhile to do a move on gear simply so that you can put stuff in a more decorative spot where you might want it. For example, if we put it here, now things begin to look a little different. You can see I'm no longer centered on that shaft because we're now in a different orientation. So if I click that, say move shaft to shaft again to the spur gear shaft, we get another re-extrusion of that original gear, and it's now a module 4.35 again, so that everything matches up. Anyway, that's how shaft to shaft works, and you already knew how move on gear and so on works. So when I'm building the clock, I'm using a combination of those techniques. I'm using the Autotrain to create the proper gear train, and then I'm using move on shaft, which automatically resizes gears so that you can share a shaft. A couple other things that you may want to take note of on this gear train calculator: the preset conversion ratios. Many of them refer to a unit. For example, if you select pi or 100 over 127, these are unitless conversions. They're assuming a 1-to-1 ratio in the input. But then I have other selections like minute to 12 hours. If you select minute to 12 hours, this is making the assumption that your input gear is turning once per minute. If your input gear was turning twice per minute, for example, you have a 30-tooth escapement, then on input rotations per unit, you could type number 2 to tell the system that your input gear is turning twice per minute, and at that point, you can use anything that says minute 2. If you have something which is turning 4 times per hour, you could enter 4. You're going to drop, meaning that you're going to drop it on a shaft which is turning 4 times per whatever unit you're trying to match. If your gear is turning 4 times per hour, then you're free to use any hour to 12 minutes, hour to day, hour to week, any unit conversion that starts with hour, because you've entered how many rotations per hour. Let's say, for example, that you wanted to use this day to moon rotation. That refers day to moon. So it means that you have to start with a day. So here you would have to enter the number of input rotations that shaft does per day. You may calculate it out at 123.56 turns on that shaft every day, and if you entered that there, then you would be free to use day to moon rotation, for example, and come up with a set of gears for that shaft that will give you the day to moon rotation. Now, something else that you need to be concerned with, primarily if you're building clocks, and that is the way that gear pairs work. A single pair of gears will give you a reversal of shafts. That is to say, if your escapement is rotating clockwise and you use a single pair of gears to shift its ratio to, say, from 2 to 1 to 1 to 1 so that you can get a second hand on it, using a single pair will reverse the direction of that second hand. So you have to be constantly aware of how many pairs you're using. Any odd number of pairs will reverse your shaft direction. Any even number of pairs will maintain it. And that's why I commonly use 2 pairs to do what I'm doing, because that keeps the second hand, minute hand, and hour hand all rotating in the same direction. If you need to get a reversal of direction, feel free to use 1 pair or 3 pairs. Your maximum allowed error is used to narrow things down. If you start with a very high maximum allowed error, you'll find here, for example, it just told me I have 1,828 ratios, which are close to what I'm asking for. If I lower that to a much lower ratio, you can see eventually we get down to 1 pair, which will match that ratio. So that's roughly how we use the Gearotic calculator. So from there, we'll start to build our clock now that you've got an introduction to that. Alright, so we have cleared the screen and we're going to start building our clock from scratch, and we'll just discuss it as I go. I'm going to make this one a 30-tooth recoil escapement, 250 in diameter, just because it sounds like a good size, and we'll add it to the project. Now, if I put a pendulum on this with a 1 second swing, this will rotate once per minute, having 30 teeth. If I put it with a, I think it's a 12-inch pendulum with a half-second swing, so a 1 second period, this would take 2 revolutions per minute, and with a 5-foot pendulum on a grandfather clock style, then this would take 2 minutes to rotate. So you have to think carefully at this point what kind of pendulum you're going to put on it. Let's go with our previous example and put a 39-inch pendulum on it. So with 30 teeth, we'll calculate that to be 1 rotation per minute so that we don't have to have any secondary shafts and so on coming off of this one. So I'm just going to right-click the ratchet then. Say set the time of master rotation, number of time, the enter time in seconds of a single rotation. We'll put 60 seconds. So now we just need to put some gear trains on here. To go to the gear trains, we go to the circular gear, and again, set up your gear type to be the type of gears that you're going to want. I've used epicycloiders here. You don't really have to, but these are very good in terms of having very good backlash capabilities, so you won't have to worry about them too much. One note here is that the actual specification for these types of gears call for rounded tips on the pinions, and they define pinions as the smaller gear. Autotrain is not smart enough as yet anyway to know which one is the smaller of the two, so it will always assume that the driver will have pointed teeth and that the driven gear will have rounded teeth, at least for now. Also, if you're going to use involute teeth, Gearotic Thoughts doesn't do backlash the way Gearotic Motion did. In Gearotic Motion, you could specify a backlash and the gears would be separated by a certain amount. That's actually an inferior way of doing backlash, and for backlash in Gearotic Thoughts, you should lower the width from 0.5 to maybe 0.48, so 48% width on the teeth. And if you do that to both gears and do a regen, you'll see that your involutes now have a half-decent amount of backlash. I personally find about 48% is good backlash for most of the stuff I do when I need backlash. So that's just a hint when it comes to using backlash. You don't need to change the width when it comes to the epicycloidals. The epicycloidals won't use them anyways. They are locked by specification to the widths that they currently are. Another thing to note is that if you were going to select a helical, knuckle, or herringbone, the program will appear to be locked up. It's using threads in various places which don't react well to giving you a progress display at the moment. That will appear soon, but at the moment it'll appear to be locked up if you're trying to do very complex items. Helicals and knuckles, depending on your resolution, can take 4 or 5 seconds each to generate. So if you're generating a complex gear train of 6 of them and then moving around and re-extruding them and so on, it could take up to 30 seconds before you actually see motion on your screen when you're creating these gear trains. So keep that in mind as you progress forward. Okay, that having been said, I've got this pretty much all set up. I picked a module 3 on mine because I know that I can cut module 3 gears on my CNC with a 3mm bit. So I tend to start off with 3, but be aware that when you start to fold gear trains into themselves, it can change the module. So always try to make it so that your gears get larger rather than smaller, unless you know that you're going to be able to cut them even if they do get smaller. So let's take a look at Autotrain since I've got everything else set up. Okay, we've already gone through here, so we know that what we're looking for. We know that our recoil is turning once per minute, so we already have a minute shaft, so we're therefore free to use any of the minute correlations. So we'll take a minute to 60 minutes. We'll take it on a 2-pair gear because, again, we want to maintain the direction of rotation of the shaft. Now, this thing is giving me a choice of 12 teeth on the wheels, 96 and 90 teeth on the pinions. This is one of the issues of making most clocks, is you're going to end up with a couple gears that are fairly large unless you use a lot of gears. The more gears you use, the smaller gears that you can end up with. And you don't necessarily have to use the fractions I've used. Minute to 60 minutes just allows me to get 2 gear pairs all at once that give me a minute hand from a second hand. But you would be free to divide that into 2 steps and make 4 gears. 4 sets of gears to get there. Downside is, of course, that you have more gears on the screen. So once you've selected the gear pair that you have, at the moment you can't shuffle the order. It is possible to maintain a ratio by shuffling the orders of these. We know we have a 12 connected to a 96 on this particular example, and then a 12 connected to a 90. And it wouldn't matter whether the 90 was with the first 12 or with the last 12. But at the moment, you're kind of locked into the choices that you were given, and they will not duplicate in the list simply switching sides. It's been fairly optimized to only give you selections of gears once rather than multiple copies of them, as you'll find in some compound gear generators. So once we have these, we'll just add them to the project. I'm going to pick the center shaft for the ratchet. And as always, you'll notice the face on my screen is facing up, so I always want to put my additions to the screen up towards in the area where his nose is, so up top of this gear, if I want them to be in front, as I do in this particular case. I won't always want them in front, of course, but if you keep your eye on the face and where the nose is, you'll always have a pretty good conception of where things are. Now, a good thing to do at this point is to pick the shaft which belongs to the final part of that gear train, and you can see when we do it that it tells us the time of rotation of this shaft is 1 hour. So that is our minute hand. It rotates once per hour, and it's a good idea to rename it just so that later on you can easily tell which shaft you're looking for. So I'm just going to rename this hour shaft so that I know it rotates once an hour. Now we can use the shaft to shaft. It is easier to use shaft to shaft if you first move an intermediate gear to a position where you're comfortable with it being before you place your final gear. You'll get the hang of this as you move stuff, but if I now click on Move on Gear, I can rotate that gear around. The other gear just slaves. And I'm going to move this to the bottom like we had in our first example. Once I've done that, now I can click our output gear, which is on the hour shaft, and I can say shaft to shaft and select our original shaft, which is just named shaft. That's on our ratchet. And when I do that, a module change occurs on this gear which suddenly had gone gray. You shouldn't need to respoke these, but there's a bug at the moment that does cause it. So when it happens, just select the gear, hit the respoke button, and you'll be back to normal. But you will notice that this gear that we just moved has changed its module. The module of it is now 3.18. It has gotten slightly larger, and its corresponding pinion has also gotten larger, or the wheel in this case. That's why it's always a good idea to be going larger than smaller, because at least you'll be able to cut it if it's going larger. If you get too small, you won't be able to machine them. But again, I'll leave that up to whoever is building this thing to decide. Okay, so now we have our hour hand, and our hour hand, or our hour shaft, is dead center to our ratchet, so everything's friendly there. We just need to go to our circular gears again, to Autotrain. And now that we have an hour shaft, we can select a ratio that uses hour as the first word. And here we go, hour to 12 hours to get our 12-hour hand. We'll do a search on 2 pairs. And again, we get all kinds that will fit. Add them to project. And I'm going to swing them right off of the hour shaft. And make sure that you swing that gear set off of the hour shaft, not off the original shaft, just because it looks in the same place. Remember that the shafts are turning at different speeds. Just because they're lined up on each other doesn't mean they're the same shaft. We're actually pretending that we have a way of getting a shaft to run inside a shaft, which most clockmakers actually can do quite well. So now we have spur 7. If I click on it, it tells me it takes 12 hours. So that's good. I'm just going to rename that object then to, let's call this 12-hour hand. Okay, so once we've done that, we can click on that 12-hour gear and do a shaft to shaft and take it back to the original shaft again. And again, you'll see that it has taken away our spokes on that object, so I'm going to click it and hit respoke. And there's our clock. All we have to do now is add 3 indicators, and since we have renamed our items on the screen to the 12-hour shaft, the hour shaft, and we have our original ratchet, there's where you would put your 3 hands. Going to our indicator screen, that's a simple matter of picking our second hand, adding it to shaft, going back to indicators, grabbing our minute hand and attaching it to the hour shaft, and finally going to the indicator, grabbing our hour hand and adding it to the 12-hour shaft. Once we do that, we hit simulate, and you can see we have a running clock and the time is right. When you click on something in the clock, it will then tell you what the rotation time is, how many rotations of the master gear, etc., etc. And a lot of this is just playing around with various factors to find things that you like. However, I think it's the fastest way that we've ever been able to build a clock. I hope you enjoy using Autotrain. Be careful when you're folding transmissions in on themselves with move to shaft. That's going to take a bit of playing with to get used to, I think. Being the designer of it, it's simple for me, but I know it's a little bit confusing until you've had some time to play with it. I'm also going to be adding many more error routines so that we can catch any of these errors that have caused some people a few crashes as they begin to play with this. Well, that's it. I hope you enjoyed watching us make a clock. I hope that you make a few of your own, and make sure that you post them to the Gearheads forum so that we can take a look at what you've done. Okay, off to the next module.